Hello.
Good morning. How are you
Morning.
guys?
All right. How are you?
Good.
Hello, Morgan. So, would anyone like to give updates? Any updates?
Just the usual reading groups going well.
Good.
Still working on this project for the ISPSM conference.
Okay.
Yeah, that's really it.
So, how is the ISPSM stuff going?
Well, I think I have a lot to say in response to some of the papers that we read for Cognition Futures.
Okay.
Yeah, I think that those were really helpful. And I see a good organization of the paper.
Yeah.
Yeah, and I should have something shareable soon.
Okay. Well, that's good. Yeah. It's always good to have to get out in front of the submission deadline so you can get feedback and
Yeah, so
Yeah.
I guess our plan for the next Cognition Futures reading group meeting was to go over what we have between my thing and Jesse's thing. So that'll be good.
Okay. Yeah, that's great. It's great. Looks like Morgan says good morning, making brunch here right now. And I assume he's not in San Francisco right now. He's in, I guess, the East Coast, from what I gathered from the Slack. So, all right. So welcome to the meeting. Jesse is in, I don't know, I can't remember what he said he was doing. I think he was attending the CBMM conference at MIT. Yeah, this is it. Well, this is the Center for Brains, Minds Plus Machines, and I think they have a conference associated with this. So, they have their Brains, Minds, and Machines group. They're doing this today, actually, seminars and events. So this is the Center for Brains, Minds, and Machines at MIT. And they have, let's see if I can find an agenda. Yeah, this is the event page. So this is, I guess, the 10th anniversary. That's cool. And, they have some people like Christoph Koch and Charles Isbell Jr. and Mark Reibert. They're all they have these videos. You can watch those. This is a symposium on intelligence and simulating intelligence. The symposium will look at the past, in particular at the advances achieved by CBMM over the past 10 years. But it'll focus mainly on the future, particularly the future of neuroscience, the future of cognitive science, and the future of AI. So that's the brains, minds, and machines, and their synergies. So it looks pretty cool. Yeah, a lot of big names because it's MIT, but also because they want to hit some weighty topics. There's interacting with the physical world, which aspects of human intelligence require embodiment, and they focus on motor control. Was it the key for the development of human intelligence? Is embodiment necessary for consciousness? The neuroscience to AI and back again, which is a review of progress and success stories in understanding visual processing, perception in primates, and replicating it in machines. And this is the open question for this is synergies. And language and thought. Is natural language the language of thought? Large language models as models of human language and thought. Are LLMs aligned with neuroscience and with human behavior? What is still missing? This is the Josh Tenenbaum session that Jesse, I think, said he wanted to be sure to attend. And then research on intelligence in the age of AI. Which critical problem should neuroscience, cognitive science, and computer science focus on now? Do we need to understand fundamental principles of learning in the sense of theoretical understanding like physics and apply this understanding to real natural and artificial systems? Similar questions concern neuroscience and human intelligence from a society, industry, and scientific point of view. So this is some names in AI: Dennis Hassabis, Jeff Hinton, Illis Kutzkever, and that's the third grouping. We had a thing, I think it was in the Wednesday meeting, where we talked about, Morgan said looked amazing. So that's good. And then, that's the link to the conference. So there's Morgan. Did you want to say something, Morgan?
Just hello.
Oh, hi.
Yes, I'm joining from the East Coast.
Oh, good.
But
good.
The conference looked great. Yeah.
So we had this comment about, I think it was at the Wednesday meeting, about whether intelligence is sort of language centric or motor centric. Or I guess the question was, is it language centric? Do you remember that, Amanda? Some people were arguing that that intelligence was kind of language centric.
Yeah, it was in the context of the On Becoming Aware book. They said that one objection to like doing phenomenology could be that you can't bracket, to use like that technical term, the impact of language.
Yeah,
that was roughly it.
Yeah. So it's interesting that like there are a couple of different types of views in the literature and running around like the study of the brain, and one of those is that a lot of cognition is motor control as well, meaning that you have motor circuits or motor networks that are controlling not only the way we move but also language. And then, of course, if you're an embodiment fan, it's this interaction between the environment and cognition. And then there's, of course, the connection between language and motor control, which is that language is a motor activity. You're moving your mouth, you're moving, there's some shared centers of the brain and so forth for motor production, speech production, and then, or even in like birds, you have motor control and the song circuit are sort of connected together in different ways. They intersect. So I think it's kind of an interesting set of points, but I don't know if people have anything to say about that. I don't know, Morgan, is there anything you want to say? Okay.
Certainly something that's been proposed a lot, in terms of motor control being kind of foundational. Yeah.
Yeah, so it's kind of interesting. A lot of these areas, well, there are a lot of kind of open things that people have proposed for how the brain is organized, how intelligence is organized. So it's just kind of, we can, I don't know, I don't really have an answer. But yeah, so that's great. Let's see. Let's look through the Slack a little bit and see what we have there. So, I mean, it hasn't been too active, but I think we can go through and see if there's anything really good in there. Let's see, bioevolution. There have been a few things in here. We go back to, what's the date today? The 7th of October. So, nothing really much. I actually got I get this artificial life newsletter from the International Society for Artificial Life. I get in my mailbox, in my email inbox, and they always have really interesting features in it. So, okay, I'm sharing my screen. So this is the issue from yesterday, I think. So 13th issue of the A-Life newsletter. They always have some really interesting features in here. And so this issue is on emergence. Emergence is a critical characteristic of A-Life systems. The whole is bigger than the sum of parts. In the same way, your contributions interact with the brains of the readers in unexpected ways, creating new ideas and possibly new discoveries. So they have, so this is run by some people at the International Society for Artificial Life. Lana Imi Mitsuyoshi, Klaus, and Gabriel. So they have some things, usually the Artificial Life Conference has an art track. And so they have this Last Film on Earth, which they're covering. This is a film, or this is intriguing questions arise when we contemplate whether machines can emulate the profound sacred experiences of living beings. Across various Amazonian cultures, belief suggests that dreams and hallucinations can serve as conduits to connect with ancestral spirits. But what does ancestrality have to do with dreams? And then they talk about this in terms of machines and artificial intelligence. And therefore, the simulation of this hallucinatory journey necessitates the intricate orchestration of computer algorithms in fiction. In our endeavor, I harnessed diffusion models, leveraging natural language prompts within the Disco diffusion script to craft an animation that emulates both the evolutionary history of life on our planet and the sensory experiences of the body during its early developmental stages. So this is kind of a fictional thing that's brought to life and is put into the world of an agent. But this is not really a scientific endeavor; it's more of a artistic endeavor. But in any case, it's still kind of quite interesting. And then someone reviewed the book The Road Not Taken, which is by Harry Turtledove. This is a science fiction story where humanity meets a race of aliens that followed a very different technological history than ourselves. From the point of view of A-Life, the story raises questions of what happens when a society finds itself stuck in a cultural local optimum. So that's cultural evolution and emergence. Then there's this special issue review, philosophical transaction special issue on emergence. This is a Zach Weinersmith cartoon that says, "Dear all-powerful computer, are there emergent properties in nature?" And the robot says, "Oh yes, emergent properties are everywhere." And then I'm assuming by emergent property you mean whenever humans see one of something and can't fathom how two of it might work, right? It's cute. It's sort of like how babies don't have object permanence. You show a human a drop of water and then peekaboo. Lots of water has currents and waves and things that they never would have guessed. Look, a large number of logic gates can reason and learn. He pulls off his top of his tentacle and you have this little circuit. And the scientist says, "Yay, again." It's just kind of, saying that we don't necessarily have the tools to think about emergence in the same way we have tools to think about other things. So this is the special issue here. Okay, so this is a special issue, Emergent Phenomena in Complex Physical and Socio-Technical Systems from Cells to Societies. And I couldn't get the link to work, so that's something, I don't know why. I guess it's not really giving me the correct link. Yeah, it wasn't put in there correctly, but that's okay. Anyways, go have a look at this special issue, the art, this newsletter. There's a link to it in the Slack in the Bioevolution channel. Then there's a paper review of assembly theory. So the ICEL Award for Outstanding Publication of 2022 at this last year's AI conference on Sapporo was on assembly theory. And then this assembly theory is like a theory of the origin of life, or the theory of emergence of life. And so assembly theory orders chemical molecules by complexity, where the complexity depends more or less on the time such molecules will need to be formed from simpler molecules. Assembly theory is proposed as a way to characterize molecules that are created by living organisms. Very complex molecules need more steps and more time to be created, so the probability that they would emerge without a living system to produce them is lower than that of simple molecules. So Lee Cronin has written a lot about this in various forms. So this is something that, if you're interested in early life or you're interested in sort of the building blocks of living systems, this is something to check out. A lot of assembly theory is sort of rooted in the sort of the chemical soup model of early life. So you have a lot of chemical compounds that get self-assembled, and then they self-assemble into larger structures like RNA molecules or DNA, and then you get replicators that then bootstrap the origins of life. And assembly theory is sort of there's a probabilistic aspect to it, and there's also the sort of a more formal theory. So then there's this A-life simulation of evolving protozoa. This is a nice little simulation here. There's a paper associated with it, real-time evolution of multicellularity with artificial gene regulation. So that's kind of an interesting paper if you're interested in the evolution of multicellularity. So that's the A-Life newsletter that I draw to people's attention. Nothing really new in the brain organoids channel, although Morgan has been posting quite a bit in there, and I thank Morgan for doing that, bringing a lot of these articles to our attention. Yeah. Brainberg Vehicles is also similarly not had very much in it, although Morgan, again, has been posting things in there. Cognition Futures is always active. Amanda's been posting there. Hussein, of course. There is this Google Doodle of, I never know how to pronounce his name, but this is the person who developed the concept of flow in psychology. Mihaly.
I was hoping you would pronounce it for me.
Oh, I don't know. I've never known how to pronounce it, but we'll just say Mihaly, okay? And so he was the sort of the developer of this concept of flow in the psychology and how, your experience, your conscious experience is a product of flow in the brain. So, we've talked about like how you have experiments that are these sort of solitary things, and then you string them together and you average them over those trials, and you get like some characterization, the mean characterization of like cognition. And his argument was that cognition actually flows over time. So you get these flows in the brain that, give you like sort of experience. There's these experiential states that are, something that play a big role in cognition. So they had a Google Doodle for his 89th birthday. And Hussein says, when going from a prisoner of war to a happiness researcher. So that's a nice, so a lot of the work and flow is on like happiness and emotion and affect and things like that. So that's interesting. We also, Amanda shared this paper so we've been talking about neurophenomenology in the Cognition Futures Reading Group. And so this is one such paper here, Neurophenomenology Revisited from Naturalism to Dialectics. So then we've been working on finishing up Google Summer of Code. And we had a meeting just yesterday, and Raj, R.V. Rajagopalan, he's been working on his project, and he presented in yesterday's meeting, which is on YouTube. He presented on his work, so the final report on it. So he's been doing things with the open source sustainability project. He's worked on like getting it up and running on the web, getting a better authentication and interface, doing some work with APIs so we can ingest data from GitHub. And then, he's been working on the simulations, especially the reinforcement learning simulation. So now there's a simulation implemented in Mesa, which is a Python version of NetLogo. So it runs agent-based models. And those agent-based models then are connected to some input data, and it can be done for a specific organization. And so it all looks very nice. And he's going to submit that in a week or two. And so he'll be around the organization for a while, hopefully. He's interested in pursuing this, continuing on. And then next summer, we'll be having a sort of a follow-up project, which will be more maintenance on the open source sustainability platform, because there's still more to do. He did a very good job this summer of knocking down some of our main improvement points, but we still have more to do on that. So finally, I'll talk about virtual reality and neurotech. And, again, this channel has a lot of interesting stuff in it. Um, Morgan and myself and Hussein have been posting in here. So there was this whole Unity debacle where they proposed to charge people for using Unity in their projects, and that I don't know how that was really resolved. But anyways, we talked about that a little bit in the open source meeting. Also, this is this EEG headband, and I bring this up because Jesse has these EEG headbands he's been playing with. We were talking about that in Wednesday's meeting. So maybe I think he's supposed to send Amanda and myself a couple of these. We're going to play around with them and see what they look like. This is just where they have like EEG sensors that they can put in, in some sort of wearable, and then you can actually analyze, these naturalistic responses. Yeah, go ahead.
Yeah, this is from my old boss at Electrical Geodesics. This is his new company.
Oh, okay,
and,
yeah.
So he was this is Don Tucker, and real pioneer in high density EEG, as you can see from my picture. I'm wearing one of Don's systems.
Oh yeah.
Anyway, so I just thought at least in the neurotech, it's always good to follow what it's called Bell Lab, for that joke. But
yeah.
It's, but a great system, or worth checking out.
Yeah. So that's people are really coming along with this technology. It's quite impressive, especially being able to put it together with like VR systems or something like that. It's really it'll be, I think, open up a lot of new avenues.
Yeah, since Hussein's not here, I'll just say that always good to check out the Galea system, which is a combo VR headset and open BCI EEG tech.
Yeah, that's the Galea system.
Yeah, I can post a link just a second.
All right. Yeah, that's great. Yeah, and then so this is more on the Unity thing, and then this is where they're talking about Elon Musk's Neuralink begins accepting human patients for trials of its brain implants. So this is something that's been going on for decades, like where people have been trying to use clinical populations to see if they can improve life for, say, like quadriplegics with brain implants. So it's like if your spinal cord has been cut due to an injury, you can restore function in the rest of your body by skipping over that injury and bringing the neural signals down into the spinal cord and to the lower part of the body. So this is, so this is that. And then it looks like Morgan posted here. Okay, so then another thing on sort of rehabilitation and neurorehabilitation on bionic arms. So they've been working on bionic arms for decades too, and a lot of the early bionic arms were pretty bad in terms of coordinating it with the rest of your body. But they've been making some strides in bionic arms. The challenge there is really to coordinate it with what you intend to do, what you want to do. You could build a very rudimentary bionic arm that would just kind of serve as a support on that side of the body, or basically move at one joint, like the elbow or something. But this bionic arm actually you can control every finger, and it uses neural signals to control the finger. So this is something that you could use in daily life to do things like grab a ball or other things. And so this is a nice advance in this area. I mean, this is an area that's again, it's always been an emerging area, but it's getting better and better as we learn more and more about how to do signal recordings and how to map them to different, this is again motor control being sort of at the crux of a lot of cognition. And of course, we have our embodiment component because you're using your body to move around the environment. And there's an interaction between the brain sending signals down to the prosthetic and then the prosthetic giving a response that we can then recognize. So then this last week, actually was last week, the MetaConnect event, the live stream event happened. So MetaConnect is a thing that happens every year in at Meta's headquarters. They usually introduce new products there, and this year they introduced the Quest 3 and some other AR glasses that they were developing. And then one of the things they did was they have this volumetric recording. So they have these volumetric avatars that they're working on. They call them codec avatars. And they had some example of Zuckerberg as a codec avatar. And he was talking about the new products and things like that. So it's kind of interesting. If you go to our Discord on VR and AR that we talked about last week, I posted some more detailed things on this. But yeah, and then Hussein was interested in that, so we talked about that a little bit. Then there's this Vision OS repository on GitHub. This is a demo project to help everyone in learning Vision OS development by creating an inspiration for fan apps. This is just some demos for Vision OS development, developed in Swift. So it's it's something that's pretty friendly to like mobile development as well. And then this is the link, Alicea.co. This is the thing that Morgan was talking about. Yeah, this is the bridge between mixed reality and neurotechnology. So this is the headset here, and then these are the neural recording sites, I guess. And yeah.
And dry electrodes, yeah.
Yeah. Good. All right, so that's virtual reality and neurotech. Zura, actually, who hasn't been around in a long time in the group, but he's he's from, I think, Georgia in the Caucasus. So he just sent a message here. Is anyone else going to attend AWE Europe by any chance, or have you gone to a past event? So AWE is a leading VR and AR events provider. This is just a conference, I guess. So yeah, I mean, there are all sorts of opportunities that come up in the Slack. So check out the Slack when you join the organization, and please, if you want to contribute to it, that's great. You can feature your contributions in a meeting. So, and thanks to everyone who contributed to the Slack channels. So it looks like Jesse's here. Anyways, yeah, welcome, Jesse. I didn't know if you were at your conference. Okay. Won't be able to say much for later, but hi. Yeah, that's good. A number of things I wanted to talk about today. I guess I'll talk about this first. This is some interesting conversation that came up. This is again on X or on Twitter, whatever they're calling it these days. And we come back to Maxim Roginski, as we sometimes do. We talk about some of the things he's been talking about on, he's kind of like a control engineer, electrical engineer, is also interested in the philosophy of mind and some other interesting topics. So this is, he's talking about here, rules are, the idea that rules are models of the world has been formalized in control theory under the name the internal model principle. So I think there was some discussion about internal models, and actually I think it was back to a paper where someone did some sort of project where they were looking at how, I think it was a large language model encoding information, and they were looking at the neurons in the model, and they noticed that some of them had what they called a representation. And then that representation would be an internal model to the model, which is like what we have in our brains, which is an internal model of the world. and they were arguing kind of that it was like a world model of the, that LLMs are basically developing this representation of the world. So the idea that rules are models of the world has been formalized in control theory under the name internal model principle. The term itself may have been coined by Murray Wanham, and we'll talk about this paper in a bit. Here he tries to generalize it and carefully delineate what the phrase internal model means. So this is from the University of Toronto Control, I guess it's the Control Lab. We'll talk about those papers in a minute. Then this is kind of moving down. Here he tries to generalize it and carefully delineate what the phrase internal model means. And then someone said something like, yes, IIRC, this is the more defensible and specific version of the Ashby-Conant good regulator theorem, in which they basically defined good regulator as one with a model. So this is relevant to what we're interested in with the ever good regulator theorem. And, this is kind of the idea that good regulation, there's often a problem in that paper. They talk about good regulation, and we've talked about this with respect to Norbert Wiener, that he talks about homeostatic versus anti-homeostatic. And it all seems kind of like, in some ways, you're just defining things in kind of valences or non-specific terms. In other words, how do you build, say, a good regulator out of mathematics if you're just using like emotional valences or value statements? So that's kind of the problem with some of the cybernetic stuff. And so in this case, they're saying that the Ashby-Conant good regulator theorem is, the definition of good regulator is one with a model. But what does that mean? Does that mean that and I think they talk about it a little bit more in detail in the paper, and oftentimes people talk about like a model of regulation as being isomorphic with the environment. But that's still, what does that mean to be isomorphic with? So, this is something that requires probably an internal model of the world, and it requires a good representation of the world. So the first paper here, I think this is the one I want. Okay. So Mitsuo Kawato, who's a roboticist, has been around for a long time. He really introduced this idea of internal models to the robotics community. And this was back in the 1990s, so it's been around a while. And the idea was that robots have like this, they perform these tasks in the world. You can get them to learn things. And they have to have some sort of internal model. So the world, of course, the robot has to be able to plan, has to be able to move in space and know where things are. So that all requires an internal model. And that internal model, in some of Kawato's papers, sort of resembles the cerebellum, which of course is used in terms of motor control and in terms of speech production and in terms of other types of behavioral regulation. So the cerebellum is a very specific structure to it. It has all sorts of, the way the cells are configured and the different connections, so you have climbing fibers and, different layers of the cerebellum that are connected, and they basically act as this time integrator. And so, these robots, they had an internal model. They were able to either forward map that internal model into the world or do an inverse modeling step where they took things from the world and encoded it into this internal model. So this paper is from the archive. This is on sort of a review of that work. So there were papers actually in the 80s and 90s. This is from Biological Cybernetics, the journal Biological Cybernetics. And it kind of talks about himself in the third person, but that's okay. In several papers published in Biological Cybernetics in the 1980s and 1990s, Kawato and colleagues proposed computational models, explaining how internal models are acquired in the cerebellum. So this is where they're actually talking about the human cerebellum, the cerebellum being like in other species as well, but they're focused on sort of the primate cerebellum largely. These models were later supported by neurophysiological experiments using monkeys and neuroimaging experiments involving humans. So they, it was a broadly primate-centric model of what's going on in the brain when you engage in motor control. These early studies influenced neuroscience from basic sensory motor control to higher cognitive functions. So these studies didn't just influence like robotics, but they also influenced neuroscience. And so a lot of our models of what the cerebellum does is also very much a part of this work as well. One of the most perplexing enigmas related to internal models is to understand the neural mechanisms that enable animals to learn large dimensional problems with so few trials. So, the problem here is that how do you learn a lot of things, a lot of features about a lot of things in very few trials? Oftentimes learning isn't about like, you can repeatedly expose an organism to its environment perpetually. They can train on it for years and years and years and learn things. But oftentimes we don't actually do that. What we do is we spend, sometimes if it's something like fear conditioning, you might only be exposed to it once and you learn an aversive behavior. Other times you have to spend more time with your environment to learn sort of the different features, the different dimensions of it and everything. So if you're a rat trying to get some sort of cheese out of a part of a maze, you have to learn the maze, then you have to figure out where the cheese is, you have to learn mental rotations, or you have to use mental rotations to get to a position. And then you have to sort of generalize that to other mazes. And so rats can do that. But they don't train the rat like infinitely. It's only relatively few trials. You can expose the rat maybe 10 or 20 times, and they'll be able to figure all this out. So this is the thing that is really perplexing to a lot of people trying to develop artificial forms of intelligence. Is how do you learn a lot in a very few number of trials? And so this is something that the internal model literature tried to reconcile by saying, well, we have an internal representation. It's an internal model that generalizes to the outside world. Consciousness and metacognition, which are the ability to monitor one's own thoughts, may be part of the solution to this enigma. Based on the literature reviews of the past 20 years, here we propose a computational neuroscience model of metacognition. So they're going from this internal model of the world, and they're saying you can model the world and you can map between the internal model and the environment. And that helps you to sort of not only encode things in the world in a very small number of trials of being exposed to something, but also that you need to have this sort of metacognitive ability to sort of integrate your cognition, So this is kind of where they're going with this. The model comprises a modular hierarchical reinforcement learning architecture. So they're using reinforcement learning of parallel and layered generative inverse model pairs. So they're using this sort of approach, sort of inspired by the cerebellum, but also this inverse modeling, where you're doing an inverse prediction of things. So you basically take the environment and you look at it and you try to reverse engineer the environment and build a representation of it. In the prefrontal cortex, a distributed executive network called the Cognitive Reality Monitoring Network, or CRMN. And so this is something, and if you're familiar with cognitive psychology, sometimes they call it the executive network more generally, but this is what they call the Cognitive Reality Monitoring Network. So sometimes if you look at papers where they do, they put someone in a virtual environment and they put them in an fMRI scanner, they can also identify features of the executive network that are involved in, recognizing reality. So put that aside for a bit. But anyways, they propose that there's this network orchestrating conscious involvement of generative inverse model pairs in perception and action. So this is where we're getting our, our models that we have inside of our brain that are used in perception, action, and this is where they're being represented in part. So there's this executive aspect of it. Based on mismatches between computations by generative and inverse models, as well as reward prediction errors. So we're taking our generative model, our generative model is our forward model. Our inverse model is the opposite of that, the inverse model. So the generative model is where you take the internal model and you generate out potential solutions. The inverse model is where you're pulling solutions out of the environment. So you have these two models that are paired and they work together in perception and action. And so you also include reward prediction errors so that the next step can be predicted. What kinds of behaviors are likely to get rewarded as a consequence of them being sort of on target versus not on target. This network, the cognitive reality monitoring network, computes a responsibility signal that gates selection and learning of pairs in perception, action, and reinforcement learning. So there's this responsibility signal. So they're just proposing like a basic reinforcement learning model where you have this, different things that are on target are rewarded, things that are not on target are not rewarded. And that's a way for you to sort of select, action selection or select the proper things to learn or to encode. So this is all kind of connected together. Usually perception and action are connected to reinforcement learning, at least in cognitive approaches. So this is not a typical thing like in the experimental world, but still, this is what they're proposing. A high responsibility signal is given to the pairs that best capture the external world, that are competent in movements, which is a small mismatch. So these are, it means that there's not a high degree of mismatch between the internal model and the external world. You want to have those things together. And this is, of course, this idea of mismatch is very similar to the idea of isomorphism. So like, you have this mapping between the good regulator and the environment. The good regulator being a good match for the environment. There should be a small mismatch or a small delta between the two models. They should be able to predict the world and provide a high degree of sort of accuracy and thus this responsibility signal. So what they're proposing is the CRMN is responsible for this regulation, this kind of internal model that then is rewarded with, some sort of signal, and then that allows us to have a model of the world that's well regulated. CRMN selects pairs with the highest responsibility signals, and these are objects of metacognition. So this is the metacognition aspect, and then consciousness is determined by the entropy of responsibility signals across all pairs. So this is where consciousness comes into play. This is like going pretty far afield, I don't know, but you have metacognition, you have these signals for metacognition, then you have this entropy of responsibility signals, which we characterize with, I guess, Shannon entropy, and then across all pairs. So this model could lead to the new generation AI, which exhibits metacognition, consciousness, dimensionality reduction, and selection of modules and corresponding representations, and learning from small samples. So we're really trying to learn from a small sample size. And of course, that's always challenging, like in statistical analysis, because the more samples we have, the better representation of the world we have. If we have a very small number of samples, then we don't really have a lot of the gaps filled in of the world that we live in, so we have to infer a lot of things, and that can contribute to a skewed internal model, skewed predictions, and not fit into this model very well. We may also develop a new scientific paradigm that enables the causal study of consciousness by combining CRMN and decoded neural feedback. So we can actually fit this into a neurofeedback paradigm as well, where we have, these brain recordings, we have maybe our virtual environment, and we can actually have this neurofeedback loop that we can then fit this model into to explain learning and metacognition. So we had some comments in the chat. Okay, so this is Amanda, and she says, how does this model compare to active inference and predictive processing? I see mismatch and prediction error, but I don't understand these models enough to recognize the differences. So I think it's probably maybe like they're kind of going in the same direction as the people doing predictive processing. So, it's really basically this idea that you have a closed loop feedback. So you have, and I would say that predictive processing is not really in the mainstream of cognitive science either. So just, I said before that people generally don't couple perception and action and reinforcement learning, which is true, but because reinforcement learning has its roots in behaviorism, so it's a bit different approach. But in predictive processing, they use sort of a proxy for reinforcement learning. They don't call it that, but they call it like a reward signal. It's feedback, but it's basically the same concept. I don't know if there's I think this is something that it's sort of a pet theory of Kawato's, and there's more maybe a robotics flavor to it. So maybe that's how it compares. Predictive processing is more like in the realm of maybe computational neuropsychology and in some other areas. But this is they both have a similar flavor to it. They both have that sort of closed loop feedback. You get a reward signal or a prediction error or something like that, and then that selects subsequent behaviors or subsequent activity in those circuits. So it's really, there is a kind of a similarity there. It's very much like what the predictive processing people are arguing, I think. And then active inference is very similar to that. It kind of fits into the idea that you're kind of actively, seeking your environment out. I don't know. I'm not familiar with the role of internal models in active inference. There's of course a representation of things, but you throw that term around a lot, so I don't know what it means really. Okay, so I hope that answered your question, Amanda. Then Jesse has a link to the Notion, so we can keep notes in the Notion here if you want to do that. Okay, so that's his paper. This is kind of goes through the history of internal models and motor control. This shows the citations of internal model in the literature. So it's been more common in the last maybe 10 years. So since about 2014, it's kind of crossed the threshold of 7,000 citations per year. And so, it's more and more common to talk about it. And then, of course, internal model plus motor control, cognition, cerebellum. In motor control, it's been, kind of a less than sort of internal model and cognition. So people have been primarily interested in modeling cognition or talking about it in terms of cognition. Fewer people are talking about it in terms of motor control, and fewer are talking about it specifically with respect to cerebellum. But it's these are the areas where they're interested in this topic. So it goes through a lot of this is an example of hierarchical and recurrent arrangements of conjugate model pairs in higher and lower levels of sensory cortices. So this is where you have a higher level model and a lower level model. You have the forward model and the inverse model. And so this is sort of the representation that we're talking about. Now, these could be within these boxes, you have sort of a distinct representation. So the forward representation is where you have a model of the world and you're predicting things in the world. And this goes off to the prefrontal cortex. This goes back to primary sensory cortex. there's at the higher level, there's a forward model. At the lower level, there's a forward model. The same thing with your inverse model, which is, of course, where you take things from the world and you try to map it into this sort of a representation. And so you can see that there's this signal that starts, let's see, where does it start? Well, it comes from the prefrontal cortex to the forward model. Then you have things going from the higher level forward to the lower level forward. And that goes from there to the primary sensory cortex. You then get things going from the forward model, lower level, to the inverse model, lower level, and then to the higher level inverse model, and then out to prefrontal cortex. So these things sit in between these areas, and it kind of generates a mismatch signal here at the lower level, which is then sort of reconciled in some way. This is another example where you have the muscles in the body, the cerebellum, and the spinal cord as this lower level. The higher level is a prefrontal, and then you have the same kind of architecture where you have a mismatch. So it really depends on where you're putting your internal model in the brain that determines kind of how the mismatch is constructed and what's regulated. So if you have something like primary sensory cortex and prefrontal cortex, it's going to be different than if you're using something like the motor system, and especially like the peripheral nervous system. So you can think of this as maybe like this is primarily mental, and this is really an embodied model of the same thing. So I mean, there's a lot of dynamics here. This is hardcore control theory, so it's not just a bunch of boxes and arrows. But anyway, in any case, you're generating a mismatch. You're using different parts of the nervous system as comparators, and you're getting an answer that then is reconciled. And they're using reinforcement learning to enforce a lot of these things. So this is what the architecture looks like. So these look like something you would see in a predictive processing paper where you have these closed feedback loops locally. They're contributing to, they're in different parts of the brain. And this is the primary sensory cortex, and then that's going down to the prefrontal cortex to the basal ganglia, which is then involved in motor control, which is what these processing loops are. And then this goes down to the cerebellum and then down to the spinal cord. And, so this just gives you an idea of where it is in the brain. So they're localizing a lot of these models in the brain. Okay, so that's that paper. Then, I promised you these other papers. So this is this person, Walter Wanham from the University of Toronto. And he has a couple papers here. This one is from 1976 in the IEEE Transactions on Systems, Man, and Cybernetics. And this is called Towards an Abstract Internal Model Principle. So this is a historical paper on this idea of internal models. As you can see from the date, it predates what Kawada was talking about, but it's going to be less refined than that. So in the abstract, it reads, in the setting of abstract automata, it is shown that a feedback regulator must incorporate a dynamic model of the exosystem, which they refer to as the outside world. So we have our outside world, which is the exosystem, to which the regulator is designed to respond. So the regulator is this thing that's not in the outside world, it's in the inside world. The result is based on a general lattice theoretic definition of the concepts of feedback and observability. So this is basically control theory related, these rigorous definitions of feedback and observability. So I think we've talked about second order cybernetics. They start talking about the observer. And so you can have observability and control theory too. So this is figure 1. This is signal flow in a feedback regulator. So this is your exosystem. And then you have two different couplings. You have a reference coupling and a disturbance coupling. So you have a reference coupling, which is how you observe coupling in the environment. And then a disturbance coupling where you observe anomalies in the coupling. And then the disturbance coupling leads to this here where you have the plant, which is the thing that's regulated, and then the actuator, and then you have this, the reference coupling goes to this Z point, the actuator goes to this U point, you have the internal model here, so you have a stabilizer and you have a controller in the middle. And that stabilizer stabilizes the internal model, and that's the controller. The plant, of course, is here, and then there's an output coupling from the plant, and then that's what we have. The plant is a term in control theory. So this is U is the control variable, Z is the regulated variable. So they come together, and you're always using the regulated variable to update the control variable. This is then figure 2. A is the open loop regulator, B is the closed loop regulator. So the open loop regulator is up at the top. So that's where we have the exosystem, and then the controller, then the plant. So the exosystem is S to the power of negative I. The controller is K, and then the plant is S plus A to the power of negative or I. So this is, I guess, -1 maybe. I can't tell. So this is where, we have the relationship between the exosystem, which is the environment, the controller, which is the regulator, and then the plant, which is the sort of how it gets regulated. Then that's the open loop system. So the open loop system doesn't have any feedback in it. The closed loop system is the exosystem, then plus I or +1, and then you have this point here, which goes to the plant. The plant equation is here, and then there's a feedback of negative I back to this. So you have an input from the exosystem that acts as this plus I, then from the plant there's negative I, so it's a feedback that's basically, I guess it's dampening the exosystem, or if the exosystem is dampened, then it reinforces it in some way. So this is the way they set this up. So there are a couple of definitions here. This is called the internal model principle, or IMP. The IMP is indeed a broadly applicable principle of feedback control, deserving of study in its own right. We recall that IMP asserts the following, and this is the definition: a regulator for which both internal stability and output regulation are structurally stable properties must utilize feedback of the regulated variable and incorporate in the feedback loop a suitably reduplicated model of the dynamic structure of the exogenous signal, which the regulator is required to possess. So suitably reduplicated model is a little bit better than, good regulation. So it requires this internal model to be a suitably reduplicated model. Whatever that means is really unclear. It could be very contextual. So it could be like that every, hair on a avatar has to be the same and in the same place, or it could just be that the avatar has hair or does not have hair. That would be suitably reduplicated for the purposes of regulation. So we don't really know what about the environment needs to be replicated to have this good control or good regulation. But basically, you need to have something to compare the external world to, and to say that this is exactly what we're dealing with, or what this is generally what we're dealing with, or whatever. The dynamic structure of the exogenous signals. So then we're interested in just the dynamic structure, not necessarily every aspect of the exogenous signals. And this is another thing that, is debatable what that means. So dynamic structure might be if there's like some sort of underlying set of features, or there's a feature space that can be boiled down to 2 or 3 dimensions, then that's maybe suitable for good regulation. Okay, so here output regulation means asymptotically zero error. That means that you have this error that approaches zero, doesn't reach zero, because you can't totally have perfect prediction, but this is output. This is kind of the definition used for servo mechanisms, where error is tracking error in response to an exogenous reference input. So like an arm, a robotic arm will move around and it'll try to get as close to its target as possible. And usually it can do that pretty accurately with very little error. There may be a little bit of noise, but it can move things from one place to another using its internal model and using like feedback from the environment. So that's the kind of output regulation we're dealing with. So if we're dealing with servo mechanisms, we can have this error that's minimized pretty easily. This is tracking error, and we can make this very explicit. You can also look at the context of process regulators. And so this is like some sort of process like a refrigerator where an error is a deviation from a set point due to an exogenous disturbance. So you have a set point in a refrigerator, the temperature it's set to. If you leave the door open all night, the refrigerator gets warmer. But if you close the door, it cools back down to, I guess, 40 degrees Fahrenheit or 4 degrees centigrade. And that, so the set point is always there. And this is, of course, what we talk about when we talk about like physiology and homeostasis in physiology, is to have this set point. You can disturb the thing in various ways, and it returns to that set point. There are dynamics associated with getting back to the set point, but it's always a place that's sort of the equilibrium point. So this is, there's error control, or there's error correction, and then there's set point sort of deviation. And so these are different types of noise you might have in your signal. These are different types, different strategies for regulation, certainly. And then, of course, the two types of error can be treated as formally equivalent. And the variable is error is under control is simply called the regulated variable. Okay. So then internal stability means that the correlated controlled system, plant together with controller, is stable. So this is where you have the plant and the controller, which is, of course, where, this is sort of the global state is the plant, and it gives the signal to sort of match what the environment is doling out or dishing out. And then the controller itself is the evaluation of that state. So whatever is coming in from the exosystem is evaluated by the controller, and then the plant sort of sets the gain on that. So the controlled system is stable with respect to internal stability in an appropriate sense. For instance, in the standard theory, the equilibrium state of the controlled system is globally asymptotically stable, which means it approaches total stability but never really reaches it for reasons that we've just talked about, because the environment has all sorts of noise in it. And you always have these different perturbations and disturbances that can drive it away from equilibrium. So it's never at equilibrium, but it tries to get as close as possible. That equilibrium state of the controlled system is globally asymptotically stable when the exogenous reference and disturbance signals are themselves fixed identically at zero or turned off. So this is where you don't have any disturbances. You can actually reach asymptotic stability, which means you're very close to total stability if you have no outside reference. So if you just turn off the exosystem, you can easily reach this level of stability. And so, the more disturbances and perturbations you have from the outside world, though, the farther away you get from this stability. So let me draw some graphs here, because I think this might be helpful. So, we're talking about asymptotic stability. We're talking about something like this, where we have a graph where we have our control variable here, and then we have our disturbance, or I guess we have our global state, which is, of course, how much the so as we get down to an S of 0, it's minimized disturbance and its stability. So we kind of go like from here, maybe down to about here. And we stay close to a value of S equals 0, and that's sort of the asymptotic regime here, where you get close to 0 but never reach 0 for reasons that, again, it's not, there's internal noise in the internal model. There's all sorts of things like that. But that's basically what we want. This is where we have our exogenous influences turned off. We don't have any outside influences. You can almost think of it as like kind of tuning something without any sort of disturbance. So you're kind of tuning the internal model to a stable state. But oftentimes in systems, they're not closed like that. They're open. And so you have this setup where you might not have asymptotic behavior. It might just kind of do this, right? So this is where you're getting different perturbations coming in at different points. And so these are, going to drive it away from that asymptotic regime. It's going to require constant regulation, and it's going to drive it down to zero, but then the perturbation will drive it back up. And so you'll see this again and again in different systems. So we have this paper called allostasis machines, and this is something back from 2021. So if you go to that paper, we kind of argue for a model like this. And this is like for an agent or for some sort of generalized physiological response. We had a conference paper on it. We might have to draw out a bigger, longer paper for this to sort of get this, make this more explicit. But this is basically the argument. So this is a closed system here. We talked about closed systems last week, where closed systems are like the closed thermodynamic system is where you might have like a system with no energy input, and it's just allowing the system to run down to increase in entropy, and eventually you end up at the lowest energy states. But an open system, of course, is where you have constant inputs from the environment, so you get energy coming in, and so it's able to sort of fight entropy. So you might see this in a living organism, for example, and something like this you might see in like a refrigerator, the closed case versus the open case. So in the lower one, the open case, our exogeny or exogenous influence might be not zero. So say it's much greater than zero. Okay, so that's where we are with that. So he kind of lays out this idea of an internal model and regulation, and this was prior, or this is just after the Conan and Ashby work. So it's kind of interesting. It's in the same era, though. So the composite system comprising the exosystem and the controlled system is the regulator. So those two things are coupled. Structural stability requires that the two basic properties of the regulator, namely internal stability and output regulation, be maintained in the presence of small parameter variations belonging to a specified and sufficiently broad class. Thus, the internal model principle states that structural stability implies that the system configuration necessarily takes the form indicated in Figure 1, which is the open loop case, or actually, this is the signal flow case. So this is sort of this closed loop feedback. And so a feedback loop in which the regulated variable actuates the controller, and where the latter incorporates a copy of the exosystem as its internal model. So what it's doing here is it has a controller, but it also has a copy. And so if you're familiar with efference copies in neuroscience, they use this concept where you have a copy of the percept and you're operating on it as a comparator. So this is where you have the reference coupling and the disturbance coupling. And then as a trivial illustration, suppose the linear plant with its input-output transfer function, which is this, is to be controlled to track a step reference signal of arbitrary amplitude. The latter can be thought of as generated by an exosystem with transfer function s-1, so it's 1, an integrator provided with a suitable initial condition or input impulse. So this is, our transfer function is an integrator. So this is again up here. This is the exosystem here, and that maps to our integrator. And then, okay, so an obvious open loop regulator is shown in Figure 2a. So this is the open loop regulator up here. The controller is just a feed-forward gain k, subject to the critical choice k equals a. Such a regulator is not structurally stable with respect to independent perturbations in the parameters k and a. And for if these varied in neighboring values in k prime and a prime, then the asymptotic tracking error in response to a unit step input will change from 0 to this term. And so we don't have any way to bring that back to 0. On the other hand, the feedback regulator of 2b, which is the feedback loop here, showing up in 2b, this utilizes integral control. This will maintain internal, i.e. loop stability, and output regulation for arbitrary parameter values, k larger than 0 and a larger than 0. So this is where we have this open system. We also have a feedback loop. So for a closed system, maybe the open loop would be suitable, but for an open system, we need a feedback loop. The integral controller is precisely an internal model of the exosystem, and both of these are assumed to remain fixed. The exosystem by a priori specification of the tracking task, and the internal model by control technology. So we make the exosystem fixed through specifying it a priori, and then the tracking task is controlled by technological regulation. So this is in a setting where you're kind of designing a controller maybe for an industrial application. So yeah, there's a lot of stuff here. Let's see. This talks about the IMP holding true in a very broad class of cybernetic situations. This intuitive idea of regulation or effective response to external stimuli. This is found in the control literature proper, but also for predictor systems with man-machine interaction, epistemology, neurology, psychology, artificial intelligence, and what they call general systems theory. So they have these citations, which are probably at this point pretty dated, but that's a nice point from the 1970s on that. Definitely kind of fits into the cybernetics literature as well as control theory. This paper is the internal modelable principle of control theory. So this is, again, kind of stating this. I think this is from, looks like 2018, but I'm not sure if this is, let's see. Yeah, they don't really talk about, they don't have the date on it other than this. But in any case, this I think may be a follow-up to that paper. So the internal model principle of control theory states that a good controller incorporates a model of the dynamics that generate the signals which the control system is intended to track. So the controller contains a model of the exosystem or outside world, which we saw in the last paper, is s to the power of -1. So that's in the, that's sort of the formal mathematical definition. So we talked about in the last paper, we talked about the control background a little bit. The implications, if we go back to the 1930s and the mathematical foundations of classical linear feedback control based in the frequency domain, the implications of that were, first of all, error feedback, where the output feedback followed by the precise differencing of the output and the input reference signal. So that's what we're doing when we compute error, is it's the difference between the output and the input. So if the input doesn't match the output, we find the difference and we use that as the correction. That can induce parameter sensitivity and final tracking error, but only at the expense of high loop gain. The second implication was that error feedback plus an internal model of the reference signal generator together reduce final tracking error to exactly 0. It ensures perfect tracking regardless of reasonable parameter perturbations, while requiring only moderate average loop gain. So loop gain is just basically that correction value, if it's required to be sort of, greater or smaller, and it requires basically less gain in the error feedback plus an internal model situation. Because you already have an internal model of the world, you can use that as the comparator, and it requires less gain, as opposed to when you don't have a model, you have to match the environment with very little information. available to you. So this is what you're doing with, in terms of gain, in terms of like that correction that produces that difference. A familiar example is the integrator component of PID control, used to track specifically step reference inputs. So the PID controller is the example they're using here. In general, the price to be paid for perfect tracking was the extra control complexity, including a stabilizing compensator specific to the reference signals to be tracked. So this is going back through the history of this. And then the internal model principle, it kind of talks about some of the converse questions. The first is error feedback, a necessary condition for good regulation or perfect tracking. The second is an internal model a necessary condition for good regulation? So, do we need error feedback? Do we need an internal model? If yes, and maybe that's yes to both of these, shouldn't these statements hold for a very wide class of regulator systems, linear or nonlinear? So if those are true and the answer is yes, and it does hold for a wide class of systems, then we can assert as the internal model principle for a very general class of systems, assertion 1, error feedback plus perfect regulation leads to an internal model. So we have this error feedback, but we can also regulate it quite well, so we can build an internal model. And then assertion 2 is structurally stable or robust, perfect regulation leads to an error feedback plus internal model. So we have this, this ability to build an internal model and achieve this kind of perfect regulation with error feedback. So we have perfect regulation that operates off of errors coming in, being smoothed out by the internal model, helping along the way. And then the second assertion is where you have structurally stable perfect regulation, which means that it's robust to different perturbations, different things the internal model has not seen before. And that requires error feedback plus the internal model. So it's almost like error feedback it's like a second order error feedback that's operating with the internal model instead of with this perfect regulation. So that's what we're talking about. And then this is the PID system here, where you have the exosystem that serves as a reference. There's error to the controller, then there's control to the plant. There's an output, but there's also feedback back to the exosystem reference, which then serves as a negative signal to the positive signal from the exosystem. So you can imagine in the world, this output goes back to the world. You're doing something in the world. You're taking in the state of the exosystem. This controller and plant are sort of figuring out what the error is and what the control signal should be. And then there's this difference in this point here where the reference signal and feedback signal interact. And then so the sort of the extraneous aspects of the exosystem are filtered out. And then that error continues to get smaller and smaller, and then it becomes, pretty close to perfect, at least in principle. So that's, I think an overview of that. I think that should be helpful to people who talk about, good regulation. And so this is kind of going back to the internal model principle and then leading up to modern neuroscience and modern robotics and how that all plays out. Okay, looks like Jesse left again. He had to go back to some sessions, I guess. Any questions about that? Yeah, no problem.
Yeah, very cool. Need to digest that.
Yeah. So I thought that was a nice discussion on feedback and some of these other things, and how we think about like how we model the brain as a product of the external world. And so this is a new paper that came out recently. This is in the Philosophical Transactions A. I don't know if it's in that special collection or not, but this is Terry Deacon, who's done a lot of stuff in like brain evolution, and I guess he's in the Department of Philosophy now at Berkeley. He was in the Department of Anthropology at one time. And then Miguel Garcia-Valdecasas, who's at the Department of Anthropology at the University of Navarra. Navarro. So this paper is called A Thermodynamic Basis for Teleological Causality. So I think they're getting into this idea of thermodynamics, but also into behavior. Let's see what they have to say. No, this is to that special issue that we were talking about in the A-Life newsletter. So this is one contribution of 13 to a theme issue, Thermodynamics 2.0, Bridging the Natural and Social Sciences, Part 1. So this is, so we show how distinct terminally disposed self-organizing processes can be linked together so that they collectively suppress each other's self-undermining tendency, despite also potentiating it to occur in a restricted way. So this is talking about self-organizing processes, terminally disposed, and I'll give an example of that. How they collectively suppress each other's undermining tendency, self-undermining tendency. So this is about emergence and some of the aspects thereof. In this way, each process produces the supportive and limiting boundary conditions for the other. The production of boundary conditions requires dynamical processes that decrease local entropy and increase local constraints. So this is what we were talking about last time with respect to living systems being these islands of that can beat entropy, I guess is the thing. So like you're decreasing local entropy, increasing local constraints, and then from that you get these organisms that serve as islands that beat entropy. So remember, we had that model of the world where we had like maybe an early Earth where we had kind of a surface of rock, and then we had our islands of sort of anti-entropy, I guess you could say. And that's what they're focusing on here. And the idea is that entropy goes down in these places. They self-organize, of course, and then the constraints go up. So when you have a living system, you have an organism. Oh, I'm sorry. Entropy goes down, constraints go up. So when you have an organism, it sort of sections off energy, and it serves as sort of an island from entropy, a refuge from entropy. But it also has a greater degree of constraint. In other words, there are fewer configurations that you can make as opposed to the outside world. So if you had some replicators out in the world, out on this barren rock that weren't sort of organismal, they'd just be replicating away. They'd be subject to entropy. But their constraints would be lower because they don't have as many parts that are integrated. And so, these things are self-organized, self-assembled. And so that's where we are with respect to all of that. Just trying to put this in a little bit more context. Okay. So the boundary condition, of course, has the boundary between these units and these islands and then the outside world, where you maybe have these naked replicators that aren't as easy to, that behave differently. Okay. Only the far from equilibrium dissipative dynamics of self-organized processes produce these effects. So we talked about dissipative systems or dissipative structures. You can think of them as maybe like a river where water cuts through the landscape and it brings energy through the landscape, and you get different living things. So if you cut a river through a desert, you can get different types of plants to bloom, different animals will come there. When the river dries up, those things go away. So it's this pulse of energy that kind of can move around or go away, and things dissipate around it, or they appear around it. So this is how we get these islands that serve sort of as refuges for other things. So these replicators could come into these islands and thrive if they're nearby, but maybe die off if they're far away. Okay. And then when two such complementary self-organizing processes are linked by a shared substrate, say the waste product of one that is a necessary ingredient for the other. So this is where we're starting to get an ecological relationship. So now these islands of entropy, let's assume that they have some sort of trophic relationship. So there's this feedback loop between one and the other. This one maybe produces waste products this island needs, and then this island produces maybe like some sort of food for this island. And again, we're just dealing with like maybe little organisms here that are more complex than replicators. So this is where we're getting this interdependency, linking together things. So there's a shared substrate, a shared energy substrate. The codependent structure that results develops towards a self-sustaining target state that avoids the termination of the whole in any of its component processes. The result is a perfectly naturalized model of teleological causation that both escapes the threat of backward influences and does not reduce teleology to selection, chemistry, or chance. So this is a problem that in the history of science and philosophy, that is this idea of teleology, it's always been pretty controversial. People have worked on it for a long time. It's basically looking at causality and looking at the flow of time and the arrow of time that we talked about earlier as being like ordered instead of things being random. But there are different ways you can approach that. That maybe suggest that there's some sort of supernatural aspect to the ordering of time. So in other words, like teleology is, maybe the arrow of time is ordered in some way. But a lot of people have kind of used that as a way to say that there's like this ultimate set of fates that, are sort of there and we're just uncovering it instead of like it being just kind of due to thermodynamic processes and things like that. So this kind of goes through the history of teleology. Spinoza argued that this doctrine of final causes turns nature complexity upside down, for it regards as an effect to which is in fact a cause and vice versa. So this idea that we have teleology, it's tempting to amalgamate these sort of theological arguments and teleological points of view, but that's so this conceptual inversion of the cause-effect relation, sometimes called backwards causation, has done much to discredit teleology. So the concept of teleology comes up in cybernetics, and it's basically the idea that things are ordered in time, and that there's this flow of things from disorder to order. So it's implied that an unrealistic state is able to influence a current physical process and bring that state into existence. This is, of course, physically implausible. The reality is somewhat less exotic. Human agents experience purposeful action as a disposition to achieve an end. So if we do some sort of behavior in the world, we have a purposeful behavior. That does not, however, mean that it influences the rest of the world. We can't say influence things with looking at them. We can't influence our own evolution just by performing behaviors and things like that. So it's important to understand causality in terms of when we talk about teleology, because we can be deceived quite easily. So, of course, human agency evolved from the less developed but nonetheless end-directed dynamics that's characteristic of all life forms. So we've kind of refined our goal-directed behaviors, especially with respect to other organisms. But, how does it happen? So I guess that's the question, one of the questions here. So the minimal basis of teleological causality should be reflected in the organization of even the simplest living systems. So we should observe this sort of teleological causality in very simple living systems, and that's what they're talking about in the paper. We should be able to identify a primitive homologue of this pre-specified form and determine how it is able to organize work to increase the probability that its form is realized. So this is where we get back to like thermodynamics and how work is organized to get to a point where we're refining behaviors and goal-directed behaviors and things like that. So if you think about an organism that's like, or an agent that is learning something new, kind of learning from learning tasks from nothing. And we talked about the internal model being a way to model the world, but at some point you have to start with a model of the world, or start from absolutely nothing. And so the idea is that you need to build up to those goal-directed behaviors. And that's kind of what they're getting at here, is that this is an aspect of thermodynamics and of self-organization, and then we need to account for this teleological mechanism that can then lead from like nothing, or this sort of self-organized beginning, to goal-directed behaviors that are optimized. So this has kind of gone through there's this idea of Rosenbluth's mechanisms. Rosenbluth, of course, is one of the authors of that paper from 1943 that we all know from cybernetics, and they talk about teleology quite a bit in terms of cybernetics. There are some other ideas of applications of this. In each case, teleological causality is treated as an epiphenomenon whose misleading appearance is due to incomplete analysis. So, although teleology is treated as a given in the social and anthropological sciences, it has become almost an unspoken rule that teleological explanations should play no explanatory role in the natural sciences. So there's this like rejection of teleology from biology ever since, some of the theories of the 19th century, where they were linked to theological arguments or arguments from creation of some type. So this is why, we don't like to appeal to teleology too much. This includes biology, where the apparently teleological concepts of function and adaptation seem indispensable to account for the metabolic and molecular processes that make a trait functional or adaptive. So one of the things about like Lamarck's theories of inheritance is that it relied on teleology, that it relied on the idea of these goal-directed behaviors driving the evolution of traits, or driving the function of traits in an evolutionary sense. So the example of Lamarckian evolution is that of a giraffe that is going to grow its neck longer and longer as it needs to eat leaves out of trees, leaves that are up high in the trees. And so the idea would be that the giraffe would expand its neck over generations because it's doing this behavior. But of course, an alternative explanation is that there were giraffes that had longer necks, that inherited the genes for longer necks, and that those individuals were selected because that's where the food was. And so the organisms with longer necks survived differentially in the populations and in subsequent generations, and you end up with giraffes with longer necks almost exclusively because that selection pressure was very strong for that. So, this is the kind of the sort of the biological aspect of this, and why people, it's kind of an uncomfortable topic in biology to talk about teleology. Also, in the anthropological sciences, there's this idea of cultural evolution, and the idea that maybe cultural evolution is like from like simple to complex societies, and there's a way of thinking about simple societies as being primitive. And of course, we don't want to think about it that way, because that's not actually the way it works. So we don't want to like impose any sort of linearity to cultural evolution. And so again, it's similarly in disrepute there as well. But nevertheless, we have these teleological mechanisms, and we have to account for them somehow. So this is what they're trying to do in this paper. So they're trying to frame it more in thermodynamic terms, explaining the operations of the simplest living processes requires straddling the distinction between mechanistic and teleological accounts. Even framed in thermodynamic terms, the teleological framing seems unavoidable. So organisms are described as performing chemical work in order to maintain themselves far from equilibrium. So organisms are doing chemical work, they're maintaining this far from equilibrium state, so they're basically creating these islands where entropy goes down instead of up. And so this is the product of a lot of chemical reactions. And those are, of course, teleological in a sense, because the chemical reaction unfolds in time. It uses energy, but it also creates reactions and things like that. So we have this teleology there. And so organisms try to maintain this far from equilibrium state at the expense of exporting entropy into their surroundings at a rate faster than they can reduce it internally. So they're doing this. This is the expense of like what they're doing. They're basically exporting entropy outside of the organism at a rate faster than they can reduce it internally. So basically, they're reducing it at a certain rate internally, right? Which is good, good because we don't want to. We're an island of entropy. We don't want to accumulate entropy inside of us. But then the environment outside of it is also gaining entropy because we're dumping it somewhere. All right, so like with a chemical reaction, we might be dumping waste, we might be dumping other things that are entropic. So the entropy out here is increasing. And the idea is that it increases greater in the environment than it does in the organism. And so eventually it will impact the organism by the organism running out of energy or, something like that. So that's what they're getting at. And so to accomplish this, they must somehow use the second law against itself. So this always comes down to Maxwell's demon, which of course is this idea that if you have two chambers of balls and they're well mixed, that you have this. So I'll draw it out actually. I don't think we've drawn out Maxwell's demon. So Maxwell's demon is of course this box. It's divided into two chambers. And it's separated by a doorway. So this doorway is controlled by a demon. And the demon actually is just some process we don't understand. But the idea is this demon is cognitively aware. And it knows that if we can sort these balls by type, we can gain, information, we can reduce entropy. So we have this well-mixed series of balls. And these balls are, of course, going to move in between chambers. So we have well-mixed series balls over here as well. And those balls can move back and forth through this doorway. And the demon basically sees if they see the state of this chamber and it sees the state of this chamber, and it tries to balance out or sort these balls. So it opens the door when, say, a striped ball comes in through the door, when it has an opportunity to go through the door. And then when a plain ball comes to the door here, it opens the door for it. So at the end of the process, you get these two chambers with perfectly sorted into plain balls and striped balls. And so this is providing order where there was previously no order. And the question, of course, is, this is, of course, a violation of the second law, because the second law implies that the opposite should hold true, that we should be able to take a well-sorted set of chambers. And we'll end up, if this demon is entropic, maximally entropic, we'll end up with a random assortment of balls. All right, so this is entropy operating, right? So it's going from these sort of these ordered states running down to randomly assorted states. This is statistical mechanics. It's nothing special. Well, what the demon is doing is it's basically reversing that process. And the demon is actually acting against entropy almost exclusively, so that this random state is sorted into this well-sorted mixture. So this is the thing that you're trying to do in self-organization. Although I wouldn't really describe it as Maxwell's demon, but you're trying to create order from disorder. Whereas in this case, you're going from well-sorted to random. And so being far from equilibrium helps here, because that's something you don't talk about Maxwell's demon. Being far from equilibrium means that you have a process that's probably chaotic enough to not end up in this random state. So you can have things that are not well sorted, but also not random. So you can have these intermediate states. And and these are kind of in the middle. And these are kind of what we mean by far from equilibrium. So we can think of our well sorted state as an equilibrium state. Our random state is a chaotic state. And again, I'm just putting these labels on because it just makes it easier to understand. And then our intermediate states is far from equilibrium. And so a regulator, of course, is we generally think about the regulator. Well, good regulation as being a product of this equilibrium state. So a well-regulated system always tends towards this equilibrium state, right? And then when the regulator fails, we think about it as a chaotic state or a random state. But there's this intermediate world that we want to think about, which is this far from equilibrium state. And, that could be where things are kind of, our sort of our state of regulation. Go back to the first graph, this S parameter, where this often goes up, pretty far from zero. And, it comes back to zero kind of over time. So it's these gigantic fluctuations. So this is what we mean by far from equilibrium. We're not asymptotic to zero, but we're also not controlled in any way. Things maybe tend towards zero, but there are these large fluctuations. And it's really a product of not really having that tight control. But of course, it's more robust to changes. So it doesn't become, it doesn't move to a random state. It stays in this far from equilibrium state. So that's what my sort of soapbox on that topic. But in this article, they provide a conceptual reanalysis of teleological processes in biology that both retain their future-oriented and directed character, yet are entirely consistent with thermodynamic principles. So they're moving towards order. They're kind of exploiting Maxwell's demon in a sense, but these are entirely consistent with thermodynamic principles. So it's not actually fighting entropy. It's just finding ways to do this. And they introduced this in 7 sections. So this is like, if you want to read the paper, you can. Section 1 reviews the challenges of the concept of teleology. Section 2 summarizes how teleological issues in biology were sidestepped by appealing to natural selection, but also, there is this concern about the supernatural entering things. And, we don't want to think of demons as like these magical beings. They're just kind of unexplained mechanisms. Section 3 provides an intuitive characterization of teleological phenomena and spells out some of the implications that end-directed processes have in thermodynamic contexts. So, when you have a goal-directed process, there's an endpoint that you want to achieve. Sometimes those happen. So sometimes you want to be at this chaotic state. Sometimes you want to go to this ordered state. This is not something that's like, conscious, or it doesn't require consciousness. It's just kind of, a system is set up in a way that's going to lead to that through maybe constraints or things like that. Terminal processes spontaneously develop towards a maximum state beyond which further change is no longer possible, driven by external conditions. And so these reflect not terminal maxima, but reflect local systems' internal stable values. So again, we're going towards this idea of bringing that control variable to zero, or at least locally to zero. Section 5 discusses how far from equilibrium self-organizing processes develop towards terminal states that are locally far from equilibrium. Okay, that means that they're locally far from equilibrium. They're in the intermediate state between random and ordered, but intrinsically unstable and dependent on extrinsic conditions. So this is kind of where they're going. They're going to talk about some of these far from equilibrium systems in this context. Section 6 explains how reciprocally linked interdependent self-organizing processes can compensate for each other's tendency to terminate. So we're talking about linked systems now, and they can reinforce the behavior of the other. So we talk about these two systems, they're islands of entropy. They do this not through like magic or through like this sort of just, constraints on their own, but they have their own constraints internally. They also have feedback, so they're interdependent and they can reinforce organizational behaviors or pro-organizational behaviors. This coupling creates a disposition to project the form of this relation into the future. So this loop, this feedback loop, has to be persistent into the future. And so this is one thing that's driving this sort of teleology, is this just the systems are living, they're defying entropy through their constraints, through their locality, and then they're interacting with one another. So they keep doing this over time, and it's not something that's conscious. It's not something driven by anything other than the dependence on each other. And then section 7, the conclusion, summarizes how this distinctive configuration of thermodynamic processes can meet the challenges identified by Bacon and Spinoza and provide an explanation of natural teleological processes free of explanatory conundrums. So that's that paper. I'll put that in the Slack for you to read more of. It's a pretty long paper, and I just wanted to give some sort of introduction to it and put it in the framework of what we've been talking about today. Yeah, Amanda's pretty interested in it. Yeah, we've been talking a little bit about that in cognition futures as well. And so there's this idea that, there really is like a disconnect, I think, between like goal-oriented behavior, the kind of behavior we study maybe in neuroscience or in artificial intelligence or in cognitive science, and some of these longer-term processes like ecology and evolution. And so kind of reconciling, or even like in terms of thermodynamics. So reconciling these views are I think, important, but it's also important to kind of think about it not in terms of what we prefer to think, but like what. So Amanda just pulled up this article on Terry Deacon, and yeah, so he's actually got a really interesting background. He's done a lot of things in biological anthropology and neuroscience and linguistics. He did this book, The Symbolic Species, back in 1997. This is where he talked about the coevolution of language in the brain. So, thinking about how human language evolved. And, we looked at these brain endocasts and talked about how in primate evolution you start to get human language capabilities. And then also thinking about language acquisition as social transmission, thinking about our social world as we were evolving from non-human primates to human primates. And so this is an important, this is a kind of one of these areas, paleoanthropology, where you don't have a lot of good hard data. You need to do things like look at fossil remains. You need to look at, like, you maybe need to do simulations. And yes, there's a healthy amount of speculation, but you did a pretty good job. That book is really good. This is I think a foundational book for thinking about the evolution of language and the brain and like symbolism and things like that. So he's done a lot of stuff. He also did some work on what he called teleodynamics, which is a complexity related thing. And then, he's been talking about thermodynamics for quite a while. So yeah, this kind of goes through entropy and some of the details around that. So yeah, so this is I'll post this in the Slack as well with the readings for today. Well, thank you for that link, Amanda. So it looks like Jesse will be joining us for sort of an update on, I knew he said he may be able to give an update on the conference, but I want him to enjoy the conference and then maybe make a report next week or something. So the final thing we're going to talk about today is we kind of talked about the control theory of the internal model. We talked about an internal model as a way to sort of represent the world. So it's in the brain, maybe. It's a controversial idea about it being in the brain. So, like I said, talking about representations is sort of a mess. An internal model of the world is like, we can maybe make the argument that motor control is controlled by an internal model, at least in robots, but it's pretty controversial to say that there are all these internal models. Nevertheless, people have proposed them. So, and then we talked, of course, about this thermodynamic basis for teleological causality, about behavior, about, other things in self-organization and how those things happen. Then we talked about how motor control maybe serves as the basis for cognition, but maybe language does too. And speech production kind of bridges those two things. Now, I want to talk about a topic called neuromechanics, and I'm going to try to get through some of this today, and maybe some of it next week. Okay. So, neuromechanics is an area where people are thinking about the brain and about the peripheral nervous system, about muscle, and about other things, and then thinking about that all in the context of sort of how the brain works, how motor control works. And so neuromechanics draws from biomechanics, which is like the study of movement, thinking about the kinetics and the kinematics of movements, so studying the movements themselves and how they're produced by the body, and then thinking about the nervous system and the neural control. And so there are a lot of connections here between neuromechanics and embodiment and these internal models and things like that. So one good reference for this is a book called The Computational Neurobiology of Reaching and Pointing. And so this is kind of a pricey book, but I mean, you can probably get it from the library. It's about 20 years old now. But it's Reza Shadmer and Stephen Wise. So they talk about this field. It's kind of an emerging field still, I guess. So this kind of focuses on reaching and pointing. So this is where you're reaching your arm out, you're pointing at things in the world. So you can see right now that there's this mechanical aspect of reaching and pointing. You move your arm, you point. There are all these mechanical things going on. You might use this for like modes of interacting with a spatial computer, or you might use it in the workplace to move things. Of course, in robotics, there's a lot of reaching and pointing analogs of human anatomy in the robotic servo arms and things like that. But there's basically this computational biology that we can understand. We can understand the computations of muscular control, of the neural signals, and then, of course, understanding what's going on in the central nervous system in terms of motor learning. So this is what kind of where they're going, and they kind of focus on reaching and pointing because it has a lot of applied relevance. So this is, I think, bridges neuroscience, robotics, bioengineering, and other disciplines. So the book begins with an overview of the evolution, anatomy, and physiology of the motor system, including the mechanisms for generating force by muscles. So muscles produce forces, and maintaining limb stability. So when you stand up, you just aren't in a zero state. Your muscles are constantly active, trying to compensate for gravity. So gravity is always trying to pull you down. You can stand there and you sway back and forth slightly to maintain your balance. So right there, we have a lot of control involved in just kind of a default state. And so this is a complex system that's keeping this going. So your posture is actually, sometimes people have problems with maintaining their posture. A lot of times older people who have muscle weakness, or they have problems with their cerebellum, they can't maintain, they either sway too much, or they can't maintain their balance, and so they fall. And so this has implications for that sort of thing as well. So the book is organized around computing locations and displacements. So we talked about the internal model and regulation, how computing locations in the environment and how those are displaced over time. So our movements have to match the target perfectly. So when we see a target, we have to move our arm there and maybe hit a target with a pointer. We can do that usually pretty effortlessly, especially if we, have normal physiological function. If we have a movement disorder, it's harder to do. Or sometimes if we displace things using a visual illusion, like a prism illusion, where we put prisms over our eyes, it can sort of act as an offset. So it's harder to learn the actual correction needs to be made to hit the target. So these are things that they explore in motor learning and in, neuromechanical responses to that. So there's a whole area of computation on this. There's also, of course, skills, adaptations, and trajectories. So your arm can make a series of possible trajectories to a target. You try to make the closest trajectory possible, but if you had someone like doing something underwater, you might have to take a slightly different trajectory because the environmental forces are acting differently on your arm. You might have like this prism effect of the water, so you can't see the target like you would see it in air. And so these require adaptations, and you can build this as a skill. So you can be very good at like making these corrections through some sort of adaptation that you develop. So there's a lot in this area that's sort of connected. Also, skill learning and motor learning are very much tied together. You learn skills by learning the sort of the motor movements, and then those become automatic. So you don't have to think about like making a motor movement when you ride a bike, for example. Once you learn how to ride a bike, you can remember how to ride a bike. You can remember how to maintain your balance, how to move the pedals, how to steer, all those things. Those are sort of encoded as you learn those things. And those aren't things you have to think about. They're this sort of procedural knowledge. And then predictions, decision, and flexibility, which talks about sort of how reaching and pointing evolves organically based on computational principles rather than a traditional structure by structure approach. So this is where they think about this problem purely in terms of computational principles. So this, again, this sort of predictive processing aspect where, it very much follows from the internal model predictive processing area. So this is a very mathematically rigorous book or approach to this. You can see that this is a version on Google Books. So if you're interested, you have this biology refresher, anatomy refresher, mathematics, physics, and neurophysiology refresher. So you need to know all those areas somewhat well. And they give refreshers on it, but it's going to involve all those areas. So it's just kind of a heads up on that. So that's the book. One of the books in the field. There's also this talk about muscle synergies. And so we've talked about this in some of the stuff we've talked about with cognition and sort of dynamical systems approaches to cognition. And we've also talked about synergetics as an approach to complex systems. So this paper is an engineering-oriented paper. And this is on muscle synergy-driven motor unit clustering for human-machine interfacing. So again, it deals with these sort of motor behaviors and how the muscle is producing outputs. And you can measure it with something called an EMG. And so these are electromyographic signals that sort of give you an indicator of sort of muscle activity, power output, things like that. EMGs can provide information on the overall activity of the innervating motor neurons in any given muscle. So motor neurons from the spinal cord will innervate muscles. They'll give a signal to the muscle, and there's certain rules of activity there that so it basically innervates the motor neurons. It sends a signal to the muscle, and then the muscle gives a particular power output, so it can control. And of course, our muscles are able to control fine movements as well as coarse movements, like if you kick your leg versus moving your fingers around an object. So, motor control is pretty flexible in that respect, at least in humans, but also globally reflect the underlying neuromechanics of human movement. So these are called muscle synergies. And of course, muscle synergies are where a bunch of muscles move together to accomplish a movement. If your muscles all acted on their own, then you wouldn't be able to coordinate your movements. So a motor synergy is where all these muscles are coordinated. So if you're walking, for example, gait has a set of muscle synergies, and your different muscles in your legs are coordinated, and the different muscles in your arms are coordinated to sway with your movement of your legs. So those are all muscle synergies, and it's very hard to consciously decouple those. But they can be decoupled in some cases, but for the most part, not. So they've applied this to rehabilitation where people have lost functionality in some of their muscles. So if you have damage to your muscles, of course, you can't make these synergies work, and so it affects movement. And so this is what they're talking about here, trying to restore some of that movement from kinematic data, which is where they're recording the data about movement, that they can determine how well you're moving and improve that performance. So that's one paper on synergies. Another paper here on synergies is the effect of motor modularity on performance, learning, and generalizability, and upper extremity reaching. So this again is the upper body where you're reaching and pointing. And again, we're going to this idea of synergies, so that muscles are working together to achieve a movement. And we can actually look at this as a dynamical behavior. We can look at the neural state, we can look at the state of the muscles, and the state of the kinematic state, which is the state of the movement. So it has been hypothesized that the central nervous system simplifies the production of movement by limiting motor commands to a small set of modules known as muscle synergies. So these muscle synergies are modules. They're kind of grouped together in terms of neural control. So motor commands are sent that are sort of cluster these muscles together in a common set of movements. And so again, you don't have to recall this as a declarative memory. You just try to walk, and you can walk if you have the ability to walk, and that's it's an automatic thing. So you do have to, of course, when you're an infant, you have to learn how to walk for the first time, and this is where it gets interesting because those muscle synergies haven't been developed yet. So there's a lot of motor learning in infancy in terms of learning to say walk. Sometimes if you've been damaged, if you've been temporarily paralyzed, or if you have damage to your muscles, maybe due to a stroke or something, you also have to learn how to walk again or how to move again. So that's another interesting case where these muscle synergies break down. But anyways, then, recently investigators have questioned whether a low-dimensional controller can produce rich and flexible behaviors seen in everyday movements. So they were able to implement muscle synergies in a biomechanically realistic model of the human upper extremity and perform computational experiments to determine whether synergies introduced task performance deficits, facilitated the learning of movements, and generalized the different movements. So they derived a set of synergies from muscle excitations from some system that they're looking at. They're looking at reaching on a plane. So it's like a plane being like a surface, and you're reaching towards targets on a surface. So it's like a single dimensional plane where you're reaching out and you're doing things. It's a very simple model, but still it requires a lot of coordination amongst the muscles. Then we compare the performance and learning rates of the controller that activated all muscles independently to controllers that activated the synergies derived from the normal reaching task. So they looked at like muscles not involved in a synergy, the muscles are all in it for themselves, versus where you actually have synergies. And so the controller based on synergies at errors within 1 centimeter of a full dimensional controller and achieve faster learning rates. So we talked about where systems can be optimized towards minimization of error. And so in like a system where you have an internal model, the internal model helps you reduce that error down to trivial levels. As it turns out, this, organizing the body in different ways through muscle synergies, through coordinated movement, can also reduce the error to trivial levels. You may or may not need an internal model for this. So you could have a muscle synergy without an explicit internal model of the world. But what muscle synergies do is they basically reduce those degrees of freedom, just as your internal model does, because you have a model of the world. some things are more probable in the world than others. And even in the self-organization example, where we talked about how there are constraints within an organism that minimize entropy. So, these are all kind of connected things. So that's talks about muscle synergies. Then there's this paper from Elaine Gorielli, who's a mathematician, et al. This is a book chapter called Neuromechanics, From Neurons to Brain. So Elaine Gorielli's been interested in building these multi-physics models of biology, where he includes different types of physics models to explain what organisms are doing, what brains are doing, what the body is doing, and so forth. And so this is kind of this multi-physics approach applied to neuromechanics. So this talks about neuroelasticity, which is sort of the elasticity of the brain, neurodevelopment, growth of neurons, growth of tissues, and growth of the brain, neurodamage, which is like damage of single neurons, and then open questions and challenges. And so they talk about some of this, some of how the brain behaves, or, in the context of, so in this case, neuromechanics is actually more about like what's going on in the brain, the mechanics of the brain, and how that relates to some of the outputs. So you have like, plasticity, you have other types of, recovering from damage and things like that. So it doesn't really involve too much about behavior, but it does involve kind of like the physics of the nervous system at multiple scales. And so that's a little bit different approach to neuromechanics. This is the Neuromechanics of Human Movement book by Roger Anoka. Roger Anoka is a biomechanist, and this is kind of another take on neuromechanics, emphasizing more on the biomechanics rather than, say, the neuromechanics or the interaction between biomechanics and behavior and nervous system function. So this is another example of another flavor of this area. This is, of course, the computational neurobiology of reaching and pointing, as we talked about. This paper is Neuromechanics, an integrative approach for understanding motor control. This is by a group of people who do things like animal behavior and building robots, building computational agents, and other things. So this is a diverse group of people. A lot of these people attend the AMAM conference, artificial or animal, the sort of, it's talking about animals and machines and adaptive movement. So this is this review kind of goes over their kind of view of neuromechanics, where they seek to understand how muscles, sense organs, motor pattern generators, and the brain interact to produce coordinated movement, not only in complex terrain, but also when confronted with unexpected perturbations. So they're interested in movement, like walking and running and other things, but like the neuromechanics underlying that. So like the muscle movements, what the brain is doing, and other things like that. So it kind of has a lot of sort of implications for prosthesis design, rehabilitation in terms of like spinal cord injury and the design of mobile robots and other agents. And so in animals, coordinated movement emerges from the interplay of descending output from the central nervous system, sensory input from the body environment, muscle dynamics, and emergent dynamics of the whole animal. So that's their approach to neuromechanics, and they talk about this in this review. So yeah, and then so that's kind of maybe a more biological approach, but then going into the applied areas. This paper is Neuromorphics meets Neuromechanics. So this kind of talks about neuromorphic engineering and taking this world of neuromechanics in the neuromorphic direction, which is designing this programmable hardware, this VLSI hardware, to implement simple models of spiking neurons, but also coupling that with skeletal muscle models, muscle spindle proprioceptor models, and other types of things that you find in the embodied system. So they're trying to take this idea of, neuromorphic design and apply it to, embodied robots that have a realistic sort of nervous system and all that. And so they're able to model some of these peripheral elements as well as a central nervous system. And then finally, this paper on a neuromechanical model exploring the role of a common inhibitor motor neuron in insect locomotion. This is from the authors of the biologically flavored neuromechanical paper, where they analyze a simplified dynamical closed-loop neuromechanical simulation of insect joint control. So they're interested in the joint control in insects. They're interested in two elements. The first is how slow muscle fibers serve as temporal integrators. So we talked about temporal integration being important for feedback and closed-loop feedback as well as open-loop feedback of sensory feedback. And two, the role of common inhibitory motor neurons in resetting this integration when the commanded position changes, particularly during steady state walking. So they're interested in these in this case, closed loop neuromechanical feedback of insect walking and moving around. And they do the steady state walking where you have perturbations, you have variations in the output of the nervous system, you have variations in the surface that the organism is walking on. And they want to understand the dynamics of this. So despite the simplicity of the model, we show that slow muscle fibers increase the accuracy of limb positioning. So there is a certain type of muscle fiber called slow muscle fibers that increase accuracy even for motions much shorter than the relaxation time of the fiber. This increase in accuracy is due to the slow dynamics of the fibers. The common inhibitory motor neurons play a critical role in accelerating muscle relaxation when the limb moves to a new position. So you can see there's an interaction between motor neurons, the types of muscles in the body, and then the movements and how they're regulated in their dynamics. So this is all kind of, you wouldn't know this unless you had this kind of model. If you just tried to model this with an internal model, you would fail because there's so much more going on at the periphery. And it's not just a matter of getting feedback from the environment, because the environment is not, mediating this control. It's actually the periphery of the organism. So it's like the limbs and the state of the power produced by the limbs and the regulation of muscle control over the limbs that are interacting with the surface that you're walking on. And then, you're interacting with your environment in different ways. So those things have to be integrated. So it's a very different approach to the internal model. It's expanding it out to the whole organism. And so, there's a lot here that can be applied to robotic control and the complexity thereof. So I see Morgan has his camera on. Yeah, so many good readings. Yeah.
The neuromechanics of from neurons to brains sounded very similar to some of the work that, again, when we were doing electrical geodesics, in terms of seeming more like capturing the physics properties of the brain itself. But super interesting, all of that.
Yeah. So, there are different ways you can do this. You have sort of behavioral oriented, maybe like, other types of ways. And then, of course, you have the brain itself where you want to get some accounting of, the physics of the brain, but also how the brain operates. And then, maybe moving that towards behavior at some point once you understand that. There are all the different ways you can characterize it. Okay. Did anyone have any other questions? Amanda, did you have any comments?
No, nothing in particular, but these were all very interesting.
Okay.
And yeah, I definitely want to dig into the longer teleology paper.
Yeah.
That was relevant for things that have come up in Cognition Futures and the Human Beings reading group. So yeah, very cool.
Yeah, we'll have to follow up on it. I thought that would be interesting to people. So, all right. So yeah, I'll post all those readings in the Slack, and we can, extend our understanding of that way.
Yeah, sounds good.
Yeah. All right. So yeah, thanks for joining us, Morgan and Amanda. And hopefully Jesse is having fun at CBMM, and we can get a report next week.
It looks such a great lineup.
Yeah.
It'd be great to hear. Yeah.
All right. Thanks, and see you next week. Bye.